Dr. Schoffer speaking here. Welcome to Orgo 2, and today we'll discuss aromatic compounds. Among others, you'll learn how to name aromatic compounds. You will learn how to not only name mono and disubstituted aromatic compounds, there are also some common names associated with this. We'll also look at a very special position with aromatic compounds, and that is the benzylic position. For the reduction portion, you'll need to have some understanding of radical mechanisms to understand how aromatic compounds can be reduced. And this chapter ends with some spectroscopic notes. So basically, it's some review we've already done in previous chapters for IR, proton, and carbon-13 NMR. But what really prevails in this chapter is the unique stability of aromatic compounds. And you may want to write this down. So we're talking about unique stability of aromatic compounds. I like to introduce this section by having students warm up and draw these couple of compounds. So we have cyclohexane, and I would pause the video here and try to draw all the structures, and then after you have drawn the structures, to then analyze the stability of these compounds and think about what you remember about what makes an alkene more or less stable, so substitution pattern, how they are ranked, and then what's unique about benzene. And that really determines so much of their reactivity, which will be covered extensively in the next chapter, chapter 18. So they are back to back. Some textbooks introduce them in one chapter, but this has been broken in two. So in this slide here, some classification. Aromatic compounds are also called arenes, and they include both benzene as well as benzene derivatives. So anything that has this component here is going to be our benzene derivative, and then we can have substituents. We can have a single substituent. Toluene is the common name, or it would also be known as methylbenzene. Here we have a disubstituted benzene. These are also known as xylene, and then we'll learn, why is this called ortho? It has to do with the positions of where these two compounds are, right? So they're kind of right next to each other in a 1-2 fashion. Benzene derivatives were originally isolated from fragrant oils. Some or most of them are odorless. On the next slide, we find the nomenclature. Basically, we have two approaches. We can follow common names, and they are accepted by UPAC as parent names. So we'll understand a little bit about parent names, and they're frequently used. So those are some structures that you need to know because they play a relevant role in aromatic chemistry, in the chemistry, the reactivity of aromatic compounds. And so you need to know that toluene is basically your methylbenzene, phenol is your hydroxybenzene, anisole is your methoxybenzene, aniline is basically the phenylamine, so on and so forth. So there's also benzoic acid, benzaldehyde, acetophenone, and we'll cover that again when we get to ketones. Benzaldehyde, that's going to be in 2 chapters. We'll look at all the aldehydes. And here's styrene. Styrene is a common precursor for making polymers in an ionic or radical polymerization step. Here's an overview of aromatic rings and how they are a common feature in drugs. So you have Lipitor. You also have this highlighted in red. You have here another molecule that has actually heterocyclic rings as well, but here's your phenyl ring. On this slide, you only have the phenyl rings highlighted in red. Make sure that you can scan these structures and then see those properties. You may want to pause here and look at these structures some more. Something that we'll touch on as well as some heterocyclic, meaning heterocyclic compounds, meaning that they have, there might be carbons in a ring, but a couple of them are replaced with nitrogen. Here's another example with nitrogen. Here also nitrogen. Turns out they do play an important role. Here we even have a heterocyclic component with sulfur, and it's going to be important for you to recognize where the electrons are located, especially as we look at some derivatives in the aromatic chapter here, trying to understand the electronics, and we'll have to decide whether something is aromatic, anti-aromatic, or non-aromatic. Another overview here: coal contains many aromatic rings fused together and joined by non-aromatic functional groups. We have here, again, color-coded all the phenyl rings. Here they are fused. It's almost like a naphthalene integrated into a much more elaborate structure. Here's another naphthalene component. Here many more linked up. So we also understand that graphite basically consists of various layers of sheets of fused aromatic rings, and here you have this shown. These compounds can also be shown with respect to just drawing the circle wherever you have an aromatic ring. But we're going to move on to another aspect here. I've integrated in this slide deck, so this does not come with the textbook, although it mentions benzapyrene. And a lot of these aromatic rings are actually carcinogenic, which means they can actually lead to the first steps that lead to cancer. And the kind of sad thing is that benzapyrene itself is not toxic, but what's happening in our body, our body has certain processes that are going, chemical reactions that are going on and on and on. And one way of just, excreting organic compounds is to make them more polar. So there are mechanisms for oxidizing this. We did not cover chapter 13 in this chapter, in Orgo 2, but here basically we have an epoxide, and that epoxide can lead to a diol, and then there can be another epoxide, but it is those epoxide functionalities that can now lead to bad chemical processes, because our bodies are full of nucleophiles, whether that's amino acids or certain DNA components. They can have a nucleophilic attack onto the epoxide, and therefore you covalently modify the structure, and that can then lead to a misreading of the DNA into the RNA, and then mistakes can basically snowball and can make a compound carcinogenic and even mutagenic. Other structures noteworthy are buckyballs and nanotubes. These are C60 spheres. We have interlocking aromatic rings. We also have a skeletal drawing here. They have unique features because the aromatic rings should be planar, and we can see that they take on different shapes. So there's some strain within these structures. They're being used in many areas. Nanotubes are more like cylinders, but you also see the 6-membered rings in here. And basically you can single, double, and multi-walled carbon nanotubes, very important for material science. And you see here a whole bunch of areas where they're being applied, not just from materials, plastics, but also biomedical applications. So let's dive into nomenclature. So how do we name these? Here it starts out with monosubstituted compounds. Basically, the substituent is being put in front of benzene. So these are all benzene derivatives: chlorobenzene, nitrobenzene, ethylbenzene. I want to briefly show you that there are even other ways of naming these. For example, if I was to use my tool where I convert a name, I could actually call something phenyl chloride, And I would get also that structure. So there's often more than one way of naming these. And we'll need to understand how we also classify these substituents, especially when we get into the next chapter. So become familiar with these structures and how we name them. Here, if the substituent is larger than the ring, the substituent becomes the parent chain. A benzene ring only has 6 carbons. Here we have 1, 2, 3, 4, 5, 6, 7. So that now takes precedence. This now becomes a heptane derivative. So heptane is the parent of this compound. And then in the 1 position, because it's attached at the end, we have 1. Of course, you could imagine that there could be a 2, a 3, and even a 4 phenylheptane derivative. Benzene rings are often abbreviated with PH for phenyl. Also a phi symbol. This is a fairly old way, but you can definitely use phenyl. Phenyl is not an element. Phenyl abbreviates everything that's shown here in red, and then you see you can just abbreviate because it kind of it saves us time to draw complex structures and also creates more clarity, especially when we're looking at various components of organic molecules. All right, so the common name for, and here we have di-substituted, so di-substituted compounds. We have 2 methyl groups on each of these phenyl rings, and they have a common name, xylene. So all of these are xylene. And now we want to understand, depending on whether they are in a 1-2 position or in a 1-3 position. Here we're dealing with, and then we have here the 1-4 position. We have adopted for these relationships, 1-2, 1-3, 1-4, additional nomenclature, and they're called ortho, meta, para. Ortho, meta, and para are used for the locations of these substituents in di-substituted benzenes. Obviously, if we go up to tri-substituted, then the numbering system itself will be much more effective. On this slide, we see some integration of common names. The common names that we have are anisole on the left hand, toluene in the middle, and then benzaldehyde on the right. Anisole is this component which was introduced a couple of slides ago, so this is something you need to be able to recall. We just talked about methyl benzenes. 1 methyl group, that's actually known as toluene. And then here's our benzaldehyde. And remember, this would be a phenyl. And this could also be drawn as CHO. This is a valid abbreviation of the aldehyde group we're going to cover in a couple of chapters. Okay. So understand these components, ortho, meta, para, various examples, practicing with your textbook questions, and each section, end of chapter section, is going to be very beneficial, so you have better recall. There's an outline as to nomenclature, very similar to all the other compounds you have encountered thus far. We want to get the parent, identify and name all the substituents. Then we want to number the parent chain, assign the locant to each substituent, give the first substituent the lowest number, and then list the numbered substituents before the parent name in alphabetical order. We ignore prefixes like tertiary or secondary, but iso plays a special role. So iso is going to be under I in the alphabetical order. Next slide shows us how to break this down for this molecule. Here we have 3 substituents. We want to now, the parent chain obviously is the phenol, highlighted here in red. This would be your 1 position. We have 2 bromines in here, so we name that. On the next slide, you then see number the parent chain 1, 2, 3, 4, 5. So this would then, as it says here, a substituent that's part of the parent, and here it is the phenol, that's going to be, by definition, your number 1. List the numbered substituents before the parent name in alphabetical order. In this case, it's the same. So this would then be 3,5-dibromophenol. Again, practice. You can pause here, and I encourage you to pause the video here, and then try to practice this right now as you've just reviewed this, and then you can check on the next slide, but try to make an earnest attempt. And for these compounds, again, there's more than one way of naming these compounds. Sometimes there are 3 ways of naming them, but here are 2 valid points. We use either the numbering or the ortho, meta, para abbreviations to have that relational indication as to what the parent compound is and where the second substituent is located. So you can check your answers. And again, practice as much as possible. Another unique feature for aromatic compounds is something that we even started out in the first week when we reviewed our pillars of organic chemistry. This is really old chemistry, first developed by August Kekulé in 1866, a long time ago. He proposed that benzene is a ring. You have to imagine at that time there was no spectroscopic method. The methods were very limited as to what chemists could learn about a compound. Often it was the composition. So using special elemental analysis, compounds can be burned, and then basically you can weigh the products. And you would know the molecular formula is C6H6. And chemists had a lot of trouble figuring out how a molecule would have a 1-to-1 ratio because they had never encountered it before. Of course, we know that the Kekulé proposed this as an equilibrium, but we do know that these are resonance structures, so we need to use the resonance arrow. And we can also then, of course, show the aromatic ring with the circle inside. So that's the aromatic compound. So Kekulé suggested an exchange of double and single bonds. That was an equilibrium. We now know better. That is actually resonance, as shown on the next slide. Please practice your curved arrows. Will be very important for next chapter when we do many electrophilic aromatic substitution reactions. There are some parallels to your alkenes chapter. If you understand the mechanisms are your friend, you will do much better. Make sure you start in the middle of where the electron pair is coming from. You can go in a circular or a clockwise or counterclockwise direction. Point in between the atoms. Be very precise about the placement of these curved arrows. Maybe you have to go back to some of the foundational chapters to review again what's happening, especially when we deal with structures that will then get a positive charge, and as we're tracing how these molecules react with electrophiles, very similar to what you encountered in the alkenes chapter in Orgo 1. And then here sometimes we have the ring, which is especially helpful when we look at symmetry, right? I had made similar points in the NMR section, and we'll take a break right here.